Right, guys, so welcome to lesson 2 on chemical equilibrium. Okay, and we're going to be having a look at the second worked example on calculating Kc. Just a recap from last week. Last week we did look at chemical equilibrium, what it was, and we also touched on the calculating the equilibrium constant, which is otherwise known as the Kc value. We looked at multiple ways to do that. Obviously, we know, again, a reminder, the formula for calculating the equilibrium constant is taking the concentration of our products divided by the concentration of our reactants, and that should give us an equilibrium constant. It should just give us a value. Okay? And that should give us an equilibrium constant value. So again, with worked example 5, we're going to be having a look at a Kc value example. And what I'm going to do is I'm going to assign this as just a sort of a exercise, almost just to get you guys back into the swing of things, to see how many steps you can remember from the previous worked example and the previous lesson, just to see if you know how to begin to approach this question. So if you don't know, it's fine. I'm not going to take any questions about it. I will go through the solution, but the reason why I just want to see how far you guys can get so that I know where everybody is. Okay, so let's have a look at this worked example 5 quickly. So the question that is posed to us is that hydrogen and iodine gas, they do react in the following equation or expression. H2 gas plus I2 gas, reversible reaction symbol there goes to 2HI gas. Okay, that means it is a reversible reaction. It's one of the reactions that we have dealt with as well. They tell us then that when 0.496 mole of hydrogen and 0.181 mole of iodine gas, they are heated to 450 degrees Celsius in a 1 decimeter cube container, the equilibrium mixture is found to contain 0.00749 mole of I2, which is iodine gas. Calculate the equilibrium constant for the reaction at 450 degrees Celsius. Alright, so having a look at this question, a couple things need to happen or take place first, okay, which is very, very similar to the solution, alright, that I'm about to do and that the textbook also has. So a couple things that does need to happen first is what I would advise everyone start doing first is always write down the reaction. Okay, so we have H2 plus I2, obviously gas and gas, and then we have our, well, that should be a bit straighter, but you get my point. And we have our product, which is HI gas as well. So what I do is when I construct my what is known as a rice table, okay, well, I have my reaction already there. Okay, then what I do is I put my R for ratio. Okay, I have my I for my initial, I have my change, and then I have my equilibrium. Okay, so I'm going to just construct the rice table. Okay.
There's another isn't there?
Talk to me, Christian. What you talk about?
Isn't there another E
This E at
for
the bottom.
equilibrium?
Yes, this E is there's another E for equilibrium, but usually I split the equilibrium and concentration thing up into two. I'll show you the split. I'll show you the split. You can actually do it like that. So you can do E for equilibrium, then you can have equilibrium mole on top here, right? Or you can split it up in this little block into two. So I'll actually show you how it's done. Or maybe I'll just do it the same way so you don't get a bit confuzzled. Because if you want a roll, I'd like to keep that roll. Okay, so we have the equilibrium mole. Okay, so I'll E mole, and then we have the equilibrium concentration. Okay, I'll just use it econ at the moment. As long as you understand what you're doing, right? That's all that matters. And you're more than welcome to write it out in full, eh? So you can write out equilibrium mole, and you can write out equilibrium concentration. You're more than welcome to do that. No one's stopping you. Absolutely no one. Okay, that's for hydrogen. And there we go. He gets the biggest slice of the pie. Okay, cool. I'm going to use another color just to fill in my values. Okay. Going back, it said that when 0.496 mole of hydrogen and 0.181 mole of I2 are heated in 450 degrees Celsius in a 1 decimeter cube container, the equilibrium mixture is found to contain 0.00749 mole of I2. So that means that initially, well, that is it's 2HI, so I've got 1 is to 1 is to 2. That's my mole ratio. Initial mole, I have hydrogen at 0.496 and 0.181 of iodine, and I had obviously 0. My equilibrium mole of I2 that I had was 0.00, I can't remember that number, 749. Okay, so this is what I have initially. Now this is just from what I was told in this piece over here. Alright, that's just what I was told. Okay, so let's go check if that part is correct. Okay, my mole ratio is correct in terms of my reactants. My first initial mole quality is correct, yes. Let's see. The equilibrium mole quantity. Okay, let's go through this equilibrium thing over here quickly. The change mole would obviously be negative x for both of these. The reason why, again, it's called negative x, just to explain that part again, because that's showing the change. Something had to have taken place here, okay, in order to get this number here, of course. Okay, and this one, the change should be minus 2x on this side, because the 2 carries down from the mole ratio. Okay, and let's just check. What I'm going to do is I'm just going to check that whole 0.81 minus x part for now, because if I am correct, then we need to take 0.181 minus x equal to that number. So I'm going to keep that number just out of the text for now. Okay. Then our equilibrium quantity mole should end up looking something like this, where we need to calculate the value of x. Okay. So in step 6, this is probably the most important step, because this is where the working comes in. Okay. So you know, for example, that the number of moles was equal to 0.00749, because this value was what they told us in the text. Right before. So again, from the table we can see that we are taking the change, which is 0.181 minus x. Okay, not minus x. Okay, it's minus x. Okay, they take this whole thing and they just put it there basically, and therefore we need to see, well, if that's what we're left with, we need to find out the value of x, so we can obviously find what the change is equal to. Okay. So if we rearrange obviously our formula, we get obviously x moves over to that side, 0.00749 moves over to the right hand side, we end up with 0.181 minus 0.00749, we get a value of 0.1735 mole. You are welcome to therefore go add that part in. Okay, so where it says negative x, you can say minus 0.1735, that can be substituted there for x. You can actually find the equilibrium quantity mole of hydrogen by taking 0.496 minus this value. You already know that that should be, that minus that must give you that value, a load already. Okay, so I can actually go add that back in, 0.00749. Okay, I know what my value of x is equal to. X was equal to 0.1735. mole? Let's double check that. Yes. So obviously that will substitute in there. That will also substitute in there. And that will be 2 times this value. Okay. And now that we have that, we need to calculate the concentration. Okay. Because the question, going back to the question up top here quickly, the question was calculate the equilibrium constant for the reaction. So we now have values for the iodine, so we can calculate the concentration for iodine, but we need to calculate what was the step 7, sorry. We now need to calculate what was the concentration or the equilibrium mole for hydrogen, as well as the equilibrium moles for the products, for hydrogen iodide, and then we need to calculate the concentrations. So let's see how we do that. Again, let's just start at this part first. I'm just going to get my calculator so we can enter in our table, because they don't exactly put in a fully functioning table there for us at the beginning. So we calculated our value of x to be 0.1735, so that value will obviously go in there. So we need our equilibrium mole, which is 0.496, minus 0.1735. We get 0.3225. Okay, and then for this one over here, minus 2 times 0. We actually don't need that value for this. Actually, we don't need that value for that actually, because we just got minus 2, and that's minus, so yeah, that's right, minus 2 x times 0.1735, well, it actually should just be 2 minus rather. Okay, we get the value of 0.347. Okay, let's double check our values. Okay, yes we do. And I don't know why I put minus there, should have been plus. That is a mistake on my part, because products always gain, reactants always get used up. Products get, there's always a gain in products and a loss in the reactants. So our values are correct for our equilibrium concentration mole, or the mole for it, equilibrium mole. Okay, and those will be the concentration as well, because remember the volume was equal to 1 decimeter cubed, so it's everything just divided by 1, so therefore it is the same. 0.3225, 0.0749, and 0.347 decimeters cubed for everything, because the volume was 1 decimeters cubed. Now we can calculate our Kc calculation, okay, which is obviously equal to the concentration of the products, which is Hi. Because of the 2 that's present here, it's going to be squared. Okay, because these two reactants have a balanced number of 1, or mole ratio of 1:1, it's just hydrogen gas, the concentration of that times the concentration of iodine. Okay, put that all over each other. Let's see, we got the 0.347 all squared, all over 0.3225 multiplied by 0.00749. Okay, I'm going to make some space here on this side quickly before everybody gets happy and decides to. Alright, there we go. Okay, does somebody have a answer for this calculation? Anybody? Anyone at all? I'll let you take some time to get me an answer, please. And then we'll take any questions that is from the people.
49,8485.
39, did you say 39 or 49? Sorry, Christian.
49.
49.
49. So we got a value of 49,85, which would be roughly equal to, if we rounded off to the nearest whole number, 50. Correct? That's why I did the whole squiggly line there, which if we rounded it off to the nearest whole number, it would have been equal to 50. That is correct. And that is our question answered. What does it mean if the Kc value is greater than 1? It means that the equilibrium lies to the right, which means there are more products than there are reactants. If the Kc value is between 0 and 1, then that means that the equilibrium lies to the left. So there are more reactants than products, which is quite summed up, or nicely summed up here in this table, all right, provided here in the Siyavula grade 12 textbook for learners. Okay, this is very, very important to remember, because they can also ask you, what can you deduce, or what can you tell or conclude by the Kc value that you just calculated? In our case, in the example above, we found the Kc value was 49.85 in this example that we went through. Okay, in the other example now, we just calculated that the example, or the Kc value, is equal to 0.21. So the first value here, this is definitely greater than 1. Okay, so in other words, here, or in that previous example above, the equilibrium lies to the right of the reaction, meaning there's more products than there were reactants. More products were made from the reactants, but we had, for the second example, an equilibrium constant that was between 0 and 1, 0.21, which is definitely between 0 and the number 1. That means there were definitely more products than reactants. We saw that when we saw that only 0.1 mole of SO2 was the change, or 0.1 mole was used, and at equilibrium we still had 0.4, and to begin with we had 0.5. So that definitely means that the equilibrium lies more towards the left. Okay, this second part here is just as important, because you will need to answer those questions that they like to add at the end of each section, which says if the Kc value had to be let's say from 0.21 had to be increased now to 0.58. Okay, what can you tell about the concentration? Write down increases, decreases, or remains the same, something like that. Okay, so this bottom part is very important, because we have a high Kc value, equilibrium constant, a very high one, so possibly greater than 1. Then that means the concentration of our products is high. All right, we mentioned the second point, the equilibrium lies to the right, and the reaction has a very high yield. All right, but if we have a low Kc value, in other words, it's closer to 0, so 0.21 is closer to 0. Okay, that means the concentration of our reactants is higher than our products, so equilibrium will lie with our reactants, in other words, to the left of the reaction, and the reaction will have, in fact, a low yield. So grade 12s, we've come to the end of our lesson for this evening on the equilibrium constant. From my side, I would just like to say thank you. Thank you for joining me in today's session. Thank you for taking time out of your schedule to come and learn about some chemistry with us and with me. I appreciate it, and we hope to see you next week, where we will learn about Le Chatelier's principle, which is the last little additive of chemical equilibrium, the follow-on from the equilibrium constant, as well as have a look at some of the graphs that have to do with Le Chatelier's principle, or that Le Chatelier aims to explain. And then before then closing off the section and moving on to acids and bases. Until next time, until next week, Monday, good night and have a good one.